Have as our speaker this afternoon, Benjamin Favier, PhD in Lyon. He then went on a tour of the UK, taking in Newcastle, Cambridge, City University, London. Sadly, he then left us to come back to France. He's CNRS position at Marseille. Benjamin.
Thank you very much, David. Thank you to the organizers for this opportunity to present this work. This is going to be a geophysical and astrophysical fluid dynamics talk, but there should be some connection with plasma physics because I'm going to talk about zonal flows, zonal jets. One of the twists is that it's going to be a mostly experimental work, so it's not the usual approach that people use in geophysical and astrophysical fluid dynamics, but this is the one I'm going to use. The reason why we want to use an experiment is that often the flows I'm considering, which are basically large-scale planetary scale flows, are better studies with like a simple reduced model with which you can do simulations. It's quite difficult to like scale an experiment down from the size of the planet to the size of an experiment. But this is what we are going to do anyway. And the reason for that is to question the validity of reduced models, basically. So there will be a lot of reduced model in this talk. So first I will use an experiment, which can be viewed as the first model reduction of the real object we're interested in. But still, this reduced experiment is still too complicated to understand. So to make sense of the measurements, we will use a two-dimensional reduced model of it. And even this reduced model is still too complicated, so we will reduce it even further using quasi-linear approach to make sense of the measurements. So there will be a cascade of reduced modeling throughout this talk. So all of the results are shamelessly stolen from Daphne Lemascarier's PhD work. She submitted a PhD a little bit more than a year ago, 1 year and a half. Yeah. So also part of the work was done by Simon Cabane when he was a postdoc with us. So my name is Benjamin Favier, and it's done in collaboration with Michael Lebars, who is also a CNRS researcher at IRFE, and Jonathan Ornou, who initially suggested to us this problem a long time ago, and Jonathan is at the UCLA. So here I'm going to talk about zonal flows in the laboratory. So there will be quite an extensive introduction, but for those of you who were there last week, it will be pretty much in the continuity of what David Ritchell presented. Okay, I'm going to use the same kind of reduced models as he used, which are relevant for large-scale planetary flows. So it will be quite an extended introduction with all the different concepts that I need for the rest of the talk. I will then present the experimental setup and show some results, and then at the end, this cascade of model reduction to make sense of the results. I have to say that most of what I'm going to say during this presentation is quite well known in our community, but here the challenge is really to see that in an experiment, not just using reduced models. Okay, so basically our main object of interest, but it's not the only one, is Jupiter. So this is an old school animation. Jupiter as viewed by Voyager 1, so a long time ago. I was not even born yet. So now Voyager 1 is far, far away, but when it crossed the orbit of Jupiter in 1979, we were able to reconstruct this nice animation where you can see that the main like first order flow that you see is this alternating flow where you have bands of flows going eastward or westward. And the rotation axis here is like so. So of course, since then, we have much nicer picture. The Juno mission is basically getting closer picture and also polar view of the planet, which we didn't see before. But basically, both of these missions, from my point of view, gave us the same information, which is the only thing I will be interested in. It's the existence of this peculiar pattern. So the way people obtain this is plots. So this is the azimuthal velocity as a function of latitude. And this is basically tracking cloud as they move in the atmosphere. And you get this kind of flow where basically the motion viewed in the frame rotating with the mean rotation rate of the planet, you have this alternating band where the flow is going eastward or westward alternatively. And this is very steady. Okay, so we measured that at several different points in time. So Cassini mission like more than 20 years ago, and then the Juno mission also. And this pattern barely moved. Okay, so it's a very steady, very robust pattern of alternating jets that are going around the planet. We have, of course, plenty of other features that I'm not going to discuss. I'm only interested into this pattern. So it's not specific to Jupiter. In fact, it's pretty common in geophysical and astrophysical fluid dynamics to have this kind of flows. So it's common to all gas giants, actually. They don't have the same feature, but they all have some kind of zonal flows. It's also the case of the Earth's ocean and the Earth's atmosphere. It's not in the same regime, mostly because the energy contained into this zonal flow is much weaker. Okay, you have much more energy into the eddy, it's a small-scale field, than in the zonal flow. Okay, so it's not in the same regime, but still, if you properly average flow in the ocean or the atmosphere, you tend to see this zonal flow. And then also you have the same kind of problem inside planetary core, which are also rapidly rotating flows. You also have a tendency for the motion. And of course, if you go beyond GAFD, in plasma, you also have a lot of zonal flows. And the key thing we try to understand is the interaction between these large-scale zonal flows and the underlying turbulence. What is the feedback mechanism between these two components? So to study this system, basically, you need two fundamental ingredients. So for GAFD, for geophysical flows, you need rotation and you need some kind of anisotropic effect, which in our community we call the beta effect. So it's either, I will explain that a little bit further, it's either due to curvature effect at the surface of a spherical planet or due to topographical effect, but both of them lead to the same kind of effect, which are anisotropic. And rotation is important to, as you will see, to get in this limit where the flow is constrained by rotation, meaning that the inertia of the fluid is weak compared to the Coriolis acceleration, which is the regime in which large-scale flows in planetary atmosphere are mostly. Of course, you can draw an analogy with the plasma physics, where this strong tendency to have an anisotropic flow would be due to the strong imposed magnetic field. And this beta effect would be any kind of anisotropic effect you have in the plasma as you move along in radius, for example. So we need these two ingredients. So let me start with rotation, just a brief recap of what rotation is doing on the turbulent flow. So obviously, here we'll use, I mean, not obviously, but here we'll use a much simpler framework we can think of. So I will use everything will be incompressible, which of course is not true for Jupiter's atmosphere, but I will do it anyway. I will consider an incompressible flow in a rotating frame. So you have the usual Navier-Stokes equation plus the Coriolis acceleration. There's no centrifugal term here because I'm either assuming it's absorbed into the pressure gradient or it's balanced by some gravitational acceleration that I didn't incorporate. So the only key ingredient is the Coriolis acceleration. So of course, if you try to build dimensionalized parameter of that, you not only have the Reynolds number, the usual ratio of inertia to viscosity, you also have another important parameter, which is the Rossby number that we've already heard about, which is the ratio of the inertia of the fluid to the Coriolis acceleration. And planetary flows are in this double limit that is very difficult to achieve both numerically and experimentally, where you have large Reynolds number, but also so lowish or very low Rossby number, depending on the limit, depending on the flows, but mostly low Rossby number. Okay, and the reason why it's difficult to achieve in the lab or in simulation is because what you want to do in the lab is simply to get very large Reynolds number flow. Once you chose your fluid, viscosity is more or less fixed. So either you want to force the fluid to move fast, or you want to build a large experiment, large length scale. Okay, so these are some limits. You're not going to be able to build a 10-meter or 20-meter large experiment. So you mostly crank up the velocity to increase the Reynolds number, which doesn't work in our case because if you do so, you also increase the Rossby number. So by doing so, eventually the flow is not going to be constrained by rotation anymore, and we don't want to be in that limit. We want to stay in the limit where rotation is always the dominant contribution. So you're left with either fixing the velocity, or so you have two options: increasing the length scale, which again I said it's not that easy, or increasing the rotation rate. But you don't have a lot of freedom to stay in this double limit at the lab scale. So that's the main challenge. And yes, well, you can also build another parameter, which is the ratio of the two. It's not independent, it's just another way of viewing it. This parameter is, of course, very small because it's a ratio of viscosity to rotation. So this is, if this is large and this is small, this is even smaller. So the Ekman number is a tiny number in application, and there's no hope for us to get the correct Ekman number. Okay, we might be able to get the correct Rossby number. We won't be able to get the Reynolds number correct. So this is even worse. Okay, we will never be able to reach the correct force balance. So an important limit of this equation is if you are in this limit, like large Reynolds, low Rossby, then there's a very simple approximation you can make, which is to basically say, okay, Reynolds is very large, I will get rid of viscosity. So you know you're not supposed to do that because of dissipation anomaly. You know that in a turbulent flow, no matter what you do, eventually this energy will be dissipated, at least in a three-dimensional flow. But here, let's do that approximation anyway. Forget about the viscosity because the Reynolds number is large. And then you can forget about inertia because the Rossby number is small. So you're left with Coriolis pressure. And then we look for quasi-steady systems. We neglect also the time derivative. So you're left with what is called, it's a fundamental force balance in geophysics. It's called the geostrophic balance. It's not a prognostic equation anymore. Okay, you cannot predict what the flow will be in the future with that equation. It just tells you that if you are in that limit, there is this strong constraint between the pressure field and the velocity field. Okay, so the Coriolis must balance the pressure gradient. So if you know the velocity field, you know the pressure field, is vice versa. But that's it. And this is a very strong constraint that is satisfied at first order in many applications. Because if you take the curl of that, then you get this celebrated Taylor-Prudhomme theorem, which tells you that curl of grad disappears, curl of this gives you this. It tells you that the gradient of velocity along the rotation axis is zero. Okay, so the flow becomes invariant along the rotation axis. Okay, it doesn't become two-dimensional, okay, because you still have three components. It's just that each of these components do not vary as you move along rotation, the rotation direction. So let me give you one of the many examples you can find of this kind of geostrophy. This is like a three-dimensional simulation of rotating convection in a spherical shell. It's in this limit where the Rossby number is small enough for the structure. You see zonal jets here, and you can see the jets tends to be invariant along the rotation axis, not along the spherical radius, okay, but along the cylindrical radius, which is the symmetry imposed by the rotation rate of the planet. Okay, and of course, on top of this, this is just a limit. So of course, you expect that this to be broken at some point, either at small scale or by other effects. For example, here you can see that I didn't talk about stratification or buoyancy or any kind of. I'm neglecting this effect. Yeah, I'm not going to talk about it. If you have additional thermal effect, for example, this is not true anymore. Okay, you have to add buoyancy and you get another balance, thermal wind balance. So here I'm going to stay in this limit where the only dynamics I have is rotation, which is a strong approximation for the application in geophysical flows, but I will do that anyway. So everything is what we call barotropic. So here basically you can forget about any kind of stratification in your atmosphere. Everything is homogeneous and there's no density effect. So the second ingredient is this beta effect. So the beta effect, funnily enough, can be derived from two completely different points of view, but in the end, the asymptotic equation is the same. Okay, so this is why I believe there is so much debate about that, is because people don't realize that sometimes they don't talk about the same effect because they use the same equation. But in fact, you can derive it from two different points of view, which is mostly historical. This is mostly the point of view of people working in atmospheric science, where they consider the atmosphere to be very shallow, which is the case on Earth, for example. The Earth's atmosphere is extremely shallow. So you start with this hypothesis where your small parameter will be the thickness of your atmosphere here, which is very small compared to the radius of the planet. That will be your small parameter to do your asymptotic analysis. The other approach is more coming from the geophysical community, like people working on geodynamo and motion inside planetary cores. They're more used to working in a 6 spherical shell, okay, with large depth in their domain, but they are in this limit where the Rossby number is very small. So the flow becomes invariant along the rotation axis, and you have this tendency of the depth of the water, of the fluid domain, varies with cylindrical radius. And this, what we call sometimes topographical beta effect, is another way of getting the same term in your reduced equation. Okay, so this is what I will describe now. We briefly recall. I'm assuming that David Ritchell talked about that last week. I will redo it quickly, and then I will also show that in this framework you get the same reduced equation for your vorticity equation. So here, in fact, for the rest of this talk, I'm not going to. So even though the experiment will be in that limit, as you will see, from the point of view of modeling, I will not really distinguish between these two approaches. Okay, so I'm not going to matter at the reduced model level. Okay, so on the left, it would be what we call 2D turbulence on the beta plane, and this would be three-dimensional rotating turbulence with topographical effect. So the first one, so it's let's say the classical beta effect, the one you will find mostly in textbooks. So it's due to the sphericity of the planet. So it's due to the fact that you have a very shallow layer. So your fluid layer is extremely thin compared to the radius of the planet. So if you fix a point in latitude, then the rotation axis is like so. But because the fluid motion locally is constrained to this tangent plane, then you don't care about the full Coriolis acceleration, but only a fraction of it. You can basically project this guy, and the first order component you get is this component along the local normal. Okay, you don't really care about the other component because the fluid cannot move in the other direction. So you get the local component of the Coriolis parameter, so the Coriolis acceleration to omega is modulated by the sine theta naught, where theta naught is the colatitude that you choose. So it's basically you get the full Coriolis acceleration in the pole and you get nothing at the equator. Okay, and this is only due to the fact that you have a very thin layer. So you can work with this, or you can expand it locally to have a nice, simple linear approximation of this variation, which leads to this. You expand your Coriolis parameter in this tangent plane, so you linearize this guy, and you just get a linear variation as you move in the south-north direction. So you get this beta naught coefficient, which depends on your position and on the planetary radius. And if you inject this linear variation of your Coriolis acceleration into your vorticity equation, so the vorticity being the one normal to the component normal to the surface, you get the usual vorticity equation. So that's just the material conservation of vorticity. Here I've kept viscosity, and you have this linear term that is coming from this. Okay, so this is a linear term where beta naught is a constant that depends on this. So it's so-called the vorticity beta plane equation, which is just usual vorticity plus this linear term. And this is basically the model we used in the following. So for the second case, topographical effect, you get exactly the same. It's just at a different way of deriving it. So now you don't have a shallow layer, so your small parameter is not the thickness of your layer. The small parameter will be the Rossby number. Okay, you're assuming that the Rossby number is very small. You have first order geostrophic balance, and then the weak departure from this balance. So you have a full 3D layer, but because the Rossby number is so small, you can assume that at first order the geostrophic balance holds, which means that your flow will be depth invariant. So what you do is you vertically average your equation. Okay, if you do so, now all variables that will be written on the board, you can view them as vertically average quantities. Okay. So this is a vertically average vorticity along this axis. This is a vertically average velocity, and so on. So if you do that, you get the vorticity equation. But now you have this term that is basically the vortex stretching term. Okay, because now you started with a three-dimensional vorticity equation. So you have the vortex stretching term that is non-zero. If you vertically average it, you get this. You have to have a divergence correction. Of course, this is. If this was a three-dimensional velocity field, it would be zero by incompressibility, but this is compressible because this is not the three-dimensional velocity field, it's the vertically average flow. And this one is not solenoidal. So you get this term, and this term you can express it through mass conservation, and it will just depend basically on the shape of your domain, with h of rho being the height of your fluid domain as you move in cylindrical radius, not spherical radius, cylindrical radius. So what it means is this is just basically associated with conservation of angular momentum. If you take a fluid column here, it has some angular momentum, and you move it sideways, well, it will compress or expand, which by conservation of angular momentum will change its vorticity depending on the local slope here that you have. So you have this divergent term here, which depends on the shape of your container. You can inject that back here, and you get exactly the same equation as before, except that now the vorticity is the vertically average component of the vorticity, and this is the radial component of the vorticity in cylindrical coordinate, and you have this term here that depends on the shape of the container. Okay, but otherwise at this level, the vorticity equation is the same as before. Okay, that is not to say, of course, that the two systems are equivalent. It's at this level of model reduction, there's no distinction between the two. Okay, so as you will see, the experiments will be in that framework. This is the simplest way we have to reproduce zonal jets in the lab using this topography effect. The natural, let's say, Coriolis effect is much more difficult to reproduce in the lab. okay, because you need variation of the Coriolis acceleration, which is difficult to realize. So we will rely on this effect instead. So from now on, I'm not going to distinguish both models. I would just assume that I have either a shallow or deep layer following this equation. This is what I will use to model the experiment for the rest of the talk. So you have material conservation of vorticity, you have this linear beta effect, you can have some friction if the flow is, if you have some no-slip boundary somewhere, you might have some Ekman pumping and leading to some friction, you can leave the viscosity, and you can have some external force. This is basically all I need for the rest of this presentation. Just a brief recap. So this term is linear, and it's of course associated to a gradient of vorticity in your system that will lead to wave kind of solution, okay, which were not existing before without this linear effect. But now, of course, if you linearize this equation, you get a non-trivial equation, which says that the time derivative of vorticity is equal to this guy. So it's not a typical D'Alembertian kind of wave equation, but still it's a wave equation. It's just that waves do not propagate in both directions; they only propagate in one direction. These are called Rossby waves, as they are associated with the gradient of vorticity either due to this variation of the Coriolis parameter or due to the fact that your water column is varying in radius. You can find wave solution you can look for plane wave solution of the equation and you get a nice dispersion relation. The only thing that is important for the rest is that so they tend to propagate westward, at least the phase propagates westward. The energy can propagate both ways. And these are basically, these waves will be present in the experiment, and the modeling I'm going to use and everything that will happen in the experiment can be understood just reasoning in terms of modulation of this simple plane wave solution. Okay, there will be some interaction between these waves and the zonal flow, and the core phenomenology that we do see in the experiment is due to coupling between these waves and the mean flow. Yeah, let me keep this drawing, and this is just an animation showing what the Rossby wave looks like. So this is like a local plane. This would be the south, this would be the north, this would be the east and the west, and you basically have a channel that is periodic in that direction, and you start with a small perturbation in your vorticity field. This is just a dimensionless parameter telling you how important are the waves. Basically, you can just look at this plot. This is where the dispersion due to Rossby wave is dominant and most visible. And you can see that the movie plays. I need to click. So you can see that all the phases are going westward. The energy is going in both directions, and so this is typically the waves that will interact with the mean flow. And these waves are due to the fact that you have a gradient in your background vorticity associated with topography or Coriolis effects. Okay, so I think I have everything. I have everything I need to go now to the experiments. So we want to basically build an experiment that reproduces as best as we can the zonal flows we see in most planetary atmosphere, as I said. So one of the key ingredients is rotation. So of course, our experiment will be rotating. And then we are not going to use the Coriolis effect, but the beta effect will come from topography. Okay, so these are the two ingredients we want to gather. So I'm not going to do a full history of this because it has very long history in the geophysical and astrophysical fluid dynamics community. So there was many different setups. Most of them are based on the same idea. But here's the only important distinction I want to make in this long history is the fact that some experiments directly force the jets. Okay, meaning that you inject some zonal momentum and then you look at how this zonal flow evolves in your system. This is not what we are going to do here. Here, we really want to have a spontaneous generation of zonal flows due to eddy-eddy interaction. Okay, so there will not be any injection of momentum, of mean zonal momentum in our system, but the zonal flow will spontaneously emerge due to the dynamics. Okay, so we will be very careful at picking a system for which there's no injection of momentum in the zonal direction. So we'll be in this indirectly forced jet limit where the energy we inject is only in the eddy underlying turbulence field, and then we want to understand how this turbulence spontaneously organized into large-scale zonal flows. So most experiments, here are three recent examples, they follow the same setup. You always have a cylindrical tank that is rapidly rotating around the vertical, and then you need some topographic effect. You need to change the height of water as you move along in cylindrical radius. So it can be done with bottom slopes like this, where you put some variable height object at the bottom of your tank. It can be due to the free centrifugal deflection of your surface. You leave your free surface at the top of your tank, and then once you reach steady state, once your tank is rotating, you have this paraboloidal deflection of your free surface. This is what we're going to use here. Or you can have a combination of both. Basically, these are always large rotating tank with some variable water column as you move along radial. And then you force the flow somehow. So this is where you have many different ways of doing it. I'm not going to go into the detail. What I want to show here is that the reason why we redid another experiment after all this long history is for the following reason, is that if you look at many measurements, experimental measurements of flow, so this is mostly always like the azimuthal position along your tank, this is the radial position, and this would be some measure of the velocity. Everyone is always seeing a strong anisotropy. Meaning you see that the flow tends to organize in something that are more or less banded along the azimuthal direction, but it's never in the regime where the first thing you see without any kind of averaging is the mean flow, like it is on Jupiter. It is always kind of meandering, where you have strong interaction between the zonal flow and the eddy. Okay, which is not necessarily the correct regime for gas giants. It might be the correct regime for the Earth's ocean or the Earth's atmosphere, but definitely not for gas giants. And the reason for that is mostly because most experiments are quasi-laminar. So these are some recent experiments. So this is the Ekman, Rossby, Reynolds number. So I won't have time to describe what this guy is. It's just a combination of this parameter. People like to use this parameter just because most experiments are order 1, okay, for this parameter. But if you look at the value of this guy in Jupiter, because the Reynolds number is so large and the Ekman number is so low, you get something that is larger, order 5. I actually don't really like this parameter because when an experiment is 1 and Jupiter is 5, you're cheating somewhere, okay? Because it's just that, I mean, you see that if you look at the other control parameter, there are orders of magnitude away, of course, and this guy is just hiding it behind a tiny number. But anyway, my point is that basically Jupiter is the key reason why this number is larger is because the Reynolds number is so large, while still being in the Rossby number limit, okay, which is easy to achieve when you have thousands kilometer length scale. It's much more difficult to achieve if you have a meter length scale. In our experiments, it's a little bit better than before. Basically, we tune everything to get a larger Reynolds number to really be at least as turbulent as we could experiment while still being in the Rossby number limit. And the only way basically to achieve this is to reduce this guy, reduce the Ekman number, which means big rotating fast. Okay, you need to increase the length scale, increase the rotation rate. There's no way around it. Okay, so this is what we did basically. So this is experiment. So it's same as before, cylindrical tank. It's 1 meter in diameter. It's rotating along the vertical axis. So we have 600 liters of water inside this tank. The upper surface is free. So in steady state, once everything is rotating, you expect this nice paraboloidal upper surface. And once you're in steady state, then you want to force the fluid to move in that frame once everything is in stationary state. If you don't do anything, of course, everything will be in solid body rotation with this paraboloidal shape, end of the story. Okay, you need to inject some energy into this system to see how energy is distributed among scales. So the way the energy is injected is by this kind of a bottom system, which is why we call this experiment the jacuzzi. So we have basically a hydraulic system at the bottom of the tank, which looks like, I'll show it after, it looks like this. So it's a complex pattern where we have pumps that force water to circulate. Okay, so we suck water in some position and we re-inject it at another position in a more or less random way. Okay, in fact, it's not so random. We have a well-defined pattern to enforce zero net injection of zonal momentum in the system. So these are 6 rings. On each rings, you have an even number of suction and injection. Okay, and this is the pattern that we use. There's 128 O's that force the fluid to circulate into this system. So we check that if you don't rotate and you activate the system and you measure the mean flow, you get some turbulent flow. But if you average zonally, there's no mean flow. Okay, the fluid does not drift in one or the other direction. It fluctuates, of course, because it's turbulent. But on average, you don't get any kind of mean rotation. So this is experiments. This is what it looks like in real time. Hopefully, there's no sound. There's no sound. So here it's rotating at 75 RPM. All of the experiment is weighing roughly a ton because you have 600 liters of water. You have all the equipment that is embarked in the rotating frame, of course, because this is the only frame that matters. And this is all roughly in real time at 75 RPM. So you clearly see the deflection of the upper surface, paraboloidal upper surface here. And once we reach this steady state, it takes like nearly an hour. Okay, because the Ekman spin-up time is quite long at this length scale. Because the only reason why the fluid spins is because of the viscous coupling at the side and bottom. Okay, mostly at the bottom, that forces the fluid to spin up. Once it spins up, it's in steady state, and we can start the experiment by activating the pump.
So Ekman circulation didn't create actual flow in your volume.
In a transient way, yes. When you start rotation, you have a complicated spin-up process with Ekman pumping and circulation. You have a complex flows, but if you wait long enough, eventually everything will be in solid body rotation. So in the rotating frame, everything is steady. So yeah, I mean, a reason why this kind of experiment is kind of difficult is you want 1 ton to rotate at 75 RPM, while still being very steady, because you don't want like your tank to slosh around and you don't want this kind of forcing. So everything needs to be quite stabilized. And so this is the rotating table is an air-bearing table that can support nearly 2 tons and can rotate to 120 RPM to reach this kind of like mechanical stability. So that if you put yourself in the rotating frame without activating the pumps, then you can measure the flow. It does nothing. Okay, actually, it's not completely true because you always have, it takes an Ekman spin-up time to reach steady state, and we wait for that long. And of course, you always have a very residual rotation in the system but it's tiny compared to the velocity we measure afterward. So for measurements, then because of this just trophic balance, the Rossby number will be very small. We expect the flow to be depth invariant. So we only measure the flow in one horizontal plane. So we put a laser plane that is cutting through the experiment. And then we look from the top with the camera, we look at this laser plane, and the flow is seeded with tiny particles that is reflecting the laser. So one of the tricks of this experiment is when you do rotating PIV measurements, so trying to measure the motion of the small particle by tracking that position, you have plenty of reflection because the laser is rotating itself. So it's a little bit like a disco problem. It's flashing everywhere. So you need to filter the laser. So the particles, they absorb light at the laser wavelengths and they reflect it and they re-emit it at another wavelength, so that we can filter and we only get the light coming from the particle without the disco effect. Okay, which is actually something that improves drastically the measurements for this kind of setup. So this is the raw movie of what the camera is seeing from the top. This is after the spin up. This is after we activate the pump for a very long time. And this is the raw motion of the particle. So this is viewed from the top. So this is basically your cylindrical tank viewed from the top. We don't see this because of refraction effect at the side of the tank. It's very difficult to have a full view. The only way would be to have some clever index matching, which is always difficult to do in such big experiments. We have 2 shadows here, just because the laser is not there. And then we have the measurement. So we track the motion of particles. These are passive. We can, by correlation, reconstruct the velocity field. You can actually do it by using your brain. Brain is quite efficient to already see the motion of the particle. And if you plug that into a PID software, you can get basically the velocity field from correlation of this particle motions. So this is an instantaneous vector field that you can get, and the only thing we are really interested in is the zonal flow. So this is what we obtain if we average over an extended period of time. You get this alternating zonal flow. So this is the zonal velocity. Blue means negative, meaning rotating slower than than the average rotation of the tank. Red means faster, and you have this alternating band that you see. Of course, if you want to make the analogy with planetary flows, the rotation axis is perpendicular to the board, so it's like looking at the planet from the pole. Okay, so if you look at Jupiter from the pole, then what you see are not jets. I mean, you still see jets, but they are correspond to rings that are, of course, going at constant latitude around the pole. Okay, so this is the same point of view for the two systems. So we do see jets. So there are different results that we can extract from this experiment, but I've chosen only one because it can be understood quite nicely and simply using a reduced model. And the result is the following. Yeah.
You stress that you don't want to inject momentum because that's a very. Why not use, for instance, waves or heat and why go through this annoying part, I guess?
Yeah. So there are two reasons. So the first reason is, so you could use like any kind of instabilities, or so it's quite difficult. So the two instabilities that have been used to force this kind of system are either thermal instabilities, so you heat somewhere basically. Also, the problem is that if you want to reach steady state, you need to heat and to cool. Okay, so heating is always easy, cooling is always a little bit more complicated. But anyway, you could do this kind of thing, but then you don't really control at which scale you inject the energy. It's controlled by the linear mechanism you've chosen to force the system. So, and it will depend on the control parameter. So you have less control using that. The other reason why we use that, and you will see later, it's because we wanted to be able to fully control the distribution of energy with radius. And the reason why it's important is because there's always an ambiguity in this system. You have this duality between 3D and 2D. So you are in a 3D system, but that behaves like a 2D system. And so when people do reduced modeling, they only have the say the vertical average, so they only have a two-dimensional system. So they just force the system homogeneously, end of the story. But if they have an homogeneous forcing in 2D, it means that it's inhomogeneous in the original 3D system. So it means you force more some regions than others. So we wanted to be able to control the radial distribution of forcing to do any kind of limits, like homogeneous forcing in 2D, inhomogeneous in 3D, which is always something that is a little bit annoying in the system. You don't know if you have to think about it in terms of a 3D system or 2D system. With this like ring setup, we can control how we inject the energy fully in radius. That's one reason. Yeah.
Maybe you said it, but I asked it. What are the vertical structures of those zonal flows?
So in the experiment or in reality? So in the experiment here, I'm not sure I will show it, but they are fully barotropic, meaning that basically they are depth invariant up to the bottom plate where you have some boundary layer reconnections, some Ekman pumping layer. But they are free, I mean, at first order, completely barotropic. So invariant along the rotation axis. So what we see on this plane, we could see it at the surface, we can see it at any point they are near invariant. So we check that by moving the laser plane, but also by simulations where, so of course, this is in the experiment. In reality, you have stratification and you have all the kind of landscape that come into the problem.
So looking at the jets, they seem to show a hint of kinks in places.
Exactly.
And the question is, what is your assessment of their stability? I mean, one might guess they're sitting near a marginal point.
So I'm not going to talk about that during this, but there's a slide about perspectives you will see where basically it's one of the things that we did not really expect. And I will show a movie that clearly show what these kinks are. It's not clear. We don't know if they are like a solitary Rossby wave surfing on the jet, or something else, but there are definitely structures we see with a nice periodicity. They come in, they burst, after they come in, they decay with a very strong periodicity, and it's not clear what these are yet. We also see them in simulation of reduced models, so it's not a three-dimensional effect. It's something that you would see in a QG approach, but it's not clear what these are.
And you checked it's not something simple like Rayleigh Coulomb. You're not sitting at the marginal point.
So it's not completely clear because, as you will see, we have two regimes of jets, and it's clear what one is. It's the one that is not relevant for geophysical application. The other one that looks more relevant, it's unclear if we're in this marginal state or not.
Can you go back to this? You say what's M8.10?
So I mean, if you look at this wavelength here, it's the forcing wavelength. And in fact, I will discuss a little bit. In these experiments, some observations are definitely correlated with the forcing we chose. Okay, some are not. And it's important to make the distinction. This wavelength here it's clearly related to the M we chose for the forcing of this particular ring. So this is an artifact of the forcing. The dynamics of this kink is not, because these kinks are not sitting on top of a forcing length scale. Initially they are, but then they launch at very large speed and they drift. So they are initially due to the forcing and then they live their own life. But definitely here, this is one of the observations that is due to the forcing.
Because you expect the Rossby wave to not necessarily also being transported at the same speed than the mean shear, and we see that in the sun.
Of course, and you will see this is the case here too. Here we are in a regime, and this is the point of the result that we discussed. The Rossby waves are super resonant. They are advected by the mean flow to become super resonant.
In a given experiment, is the pattern the same, or is the pattern always changing in time as well?
The forcing pattern.
Yes.
The forcing pattern is a very important point. The forcing pattern is steady. Okay, so there will be an important question at the end, which is, does it matter to have a steady forcing versus, let's say, an instability, which will live in a frame advected with a zonal flow? Here, no matter what the zonal flow, our forcing pattern is still the same, the rotating frame, which is something that is typical of our experiment, which might not be the case I mean, it's probably not the case in planetary application. But yeah, so this is a very important distinction. And I think there is a very important study to be made about distinguishing between this kind of forcing and more realistic forcing, like instability-like forcing, where the forcing can be strongly affected by the existence or not of zonal flows. It's not really the case of our setup. But you will see the importance of the forcing a little bit
I
later.
just want to understand if the numbers of rings that you see is linked to the number of rings you have in your forcing.
So that's what I will show here. Here, yes, and the second regime, no. So in this regime, which is the first regime, everything is due to the forcing, and it's the classical picture of a converging momentum due to eddies. And this is a classical picture of jets that you will see that we believe is not relevant for applications, but still the one we see, that's the one. So here what I will do, I will just show you two different regimes, and the control parameter will be the amplitude of our forcing. Okay, so we have like a weak, moderate Reynolds number regime, and then a strong, high Reynolds number regime. So at moderate Reynolds number, so what you will see here is the zonal velocity, again, viewed from the top, and this would be a movie. So this is just after we turn on the pump, and this is what the system looks like. So very quickly, after just a few rotation time, you see the emergence of clear zonal flows, and you can see that there's 1, 2, 3, 4, 5, 6, and we have 6 rings. Okay, so this regime is what we call the directly forced regime. So the zonal flow is not directly forced, but each jet is sitting on top of each ring. Okay, so this is clearly a regime where the response of the system is directly correlated to the force. Okay. But it's not the only regime we see. If we crank up the forcing, eventually we reach this regime. Initially, it's the same, 6 rings. Then, if you wait long enough, you start to have merging, okay, and drifting. You can see some jets are being absorbed by the other one. You start to see these kinks propagating from time to time. And now the jet is much stronger in amplitude and also living on a larger length scale. Then you don't have 6 jets anymore. You only have perhaps 2 or 3. And you can track where these jets are, and they are not always at the same position, and they are not always sitting on the top of a forcing ring. Okay, so they live their own life, and you can repeat the experiment many, many times. You won't get always the same pattern. Okay, you have a strong multi-stability in that regime, which you don't in the first. In the first, you can repeat the experiment tens of times. You always get the same pattern sitting on your forcing pattern. Yeah.
And if you were to wait for very long times, would you have an asymptotic collapse?
So that's very difficult to answer experimentally. So these experiments that typically take already, this is basically a few hours of runtime of the experiment. You have the spin-up time, then you have to activate the pumps, wait for steady state, do your measurements. Measurements are very heavy because we do PIV measurements, which we want to be able to measure all velocity length scale. So we need like a high frame rate of acquisition to be able to measure all the velocities. and over very long time. So it's like a we want to have the long time evolution of the jet, but on top of that, we still have turbulence to resolve. So we are limited in the amount of time we can achieve. It's still not completely ridiculously small compared to the viscous time scale of the problem, which of course for real application is asymptotically long, but for experiment it's not. So we still think we are in a steady state, but there's no way to prove that. Okay.
The question I wanted to ask you is that when you stop forcing, how long does it take to the system to go back to solid body rotation? So
this you can clearly compute, and it's compatible with this simple Ekman time scale. Okay. So this is the first regime. So this is the radial position versus time, and this is showing the azimuthally average zonal flow. So you have your so you don't see this jet so much because it's close to the center, but you have 1, 2, 3, 4, 5, 6 jets. They are quite steady, and you can compute the energy contained into this mean flow here, and the energy into the residuals, so the fluctuation, that have a 0 zonal average, and you can see that the energy in the zonal flow is very small compared to the fluctuation. So in this regime where basically most of the energy is into eddies, and this is just seen because you average but it's not strong enough to dominate the system. So in regime 2, you can see you have a bifurcation. You start on regime 1 with the 6 rings, but they are not stable. They very quickly merge until you reach this hopefully asymptotic, steady regime where the jets are much stronger. And now the energy contained into the mean flow is comparable to the one you have in fluctuation. Okay, so forcing stronger, you're increasing the Reynolds number, which is not ideal because you also change the Rossby number. But that's spinning faster would be a pain because then you have to wait for the parabola to equilibrate. So we can't do that. So the only control parameter we have is increasing the forcing. We change both Reynolds and Rossby, but here the effect we see is mostly a change of Reynolds, not a change of Rossby. And the interesting observation is that one is if you do continuous sweep in parameter space, so you start from this where you have your 6 jets sitting on top of your forcing, and you gradually increase. This is basically a measure of the forcing. You gradually increase the amplitude. You go through this quite sharp transition where the state jumps from this state to one of these. So these states are statistically the same. It's just that the location of the jets are different. Okay, so not the same. But if you look at the energy contained into the mean flow, it's the same. They are statistically the same, but correspond to different realization of the same state. And they all sit somewhere around here. And then you can use the other game. Of course, you see me coming when you do that. You go from regime 2, you decrease the forcing, and you go back. But if you do that, you jump back, but not at the same location. Okay, so you go from this strong jets regime to the weak jets regime, but late. Okay, so there's clearly a bistable region here between the two branches. Okay, so you have some kind of subcritical transition between the two states, the state where you have weak jets and the state where you have strong jets. In this band, both coexist depending on your initial condition. And this is what I'm going to explain using a reduced model, purely 2D quasi-geostrophic kind of model, which is enough actually to explain all of this. Okay.
The hexagon shape is like Saturn.
Yeah, so you could say that, but on this ring there are six forcing. So it would be a little bit cheating to say, oh, it's like this. But yes, you could play that game. Okay, so let's do a little bit of circular modeling. As I said, everything will be done in this quasi-geostrophic limit. So only using vorticity equation. Here it's depth average vorticity, but as I said, I don't really care about it. So you just have material conservation, the linear beta effect, and then friction, viscosity, and forcing. So you could argue, well, I mean, is it relevant? Okay, are you in the limit where this approach makes sense of your experimental observation? So it's actually not a simple question, but I will make a long story short. These are experimental measurements of different quantities, the fluctuating zonal flow, fluctuating radial flow, vorticity, and Reynolds stresses of the experiment when we activate one ring. Just everything is in solid body rotation. We activate one ring, and just after the activation, we look at what the response of the system is above the forcing line. And then on the right, this is the same thing, but solving this equation. Okay, the only free parameter is basically the amplitude of your forcing, which we get from the experiment. Okay, so if you do that, you get this numerical response. Everything is on the same color scale. Okay, so this will be enough for today to justify that they look similar. Of course, there is a lot of debate hidden behind that, but for today, it's enough for me to say that the fluid response we see in the experiment is compatible with quasi-geostrophic kind of response. It's not exactly true, of course, but for today, it's enough. So what we only really care about is the mean flow, the mean zonal flow. Okay, that's what we want to model. So in fact, it's natural to do some kind, as usual, a Reynolds decomposition. Okay, we will decompose our flow into a mean zonal flow plus some participation, and we work with this decomposition. So we start with the vorticity equation. I will do everything Cartesian. Okay, of course, experiment is not Cartesian, it's cylindrical, but in fact, curvature terms are all like high order corrections. Okay, you can take them into account. I'm not going to change qualitatively what I'm going to say. So I will work with Cartesian, where y is south-north and x is the east-west. So you decompose your velocity field to a mean zonal flow. This is the zonal average here, plus some fluctuation. You inject that back. You can compute the equation for the mean zonal flow, u. So it's just due to, and it's driven by Reynolds stresses, okay, which are coming from the fluctuation here. This term does not contribute. I've kept the friction here. This is the mean friction. I've dropped viscosity because the main dissipation in our system is not through viscosity, it's through viscous drag with the bottom, which is through Ekman pumping, which is in this model, in this quasi-geostrophic model, it's a linear term, which is this guy. So I've kept it. This disappears, and our forcing does not project onto the mean zonal flow. So we have a very simple equation. We accept a steady state, which is a balance between eddy stresses and friction. Okay. So it's quite simple. Of course, we don't know what that guy is. As usual, we have to close the problem to parameterize it. And here, basically, I will just try to convince you that you can derive quasi-analytically this guy, just assuming that the first of the response are Rossby waves. Okay, but you need to take into account one thing: the feedback of the zonal flow onto the zonal waves, which is the main ingredient you need. So for the first regime, it's quite simple because, in fact, you can look at the fluid response that you have on top of a ring when you activate it, and you see that you have Rossby waves that are radiated away, and it's a classical textbook case where you have a line of force in an infinitely homogeneous beta plane. Rossby waves are radiating, and this leads to a convergence of momentum where you force the system, which leads to prograde acceleration. So basically, you can look at how the component of the velocity alternate on top of the forcing region, and that will lead to a negative divergence, or a positive divergence of the Reynolds stress, which leads to prograde acceleration on top of this ring. Okay, and then by reaction, you get a retrograde jet on the flank of your line of force. So this is a textbook case of you force, you mix your potential vorticity, you have waves radiating away, momentum is getting tuned into your mean flow, and then you have a retrograde flow on the flank. So this is the first regime where you can clearly see that the prograde flow is sitting exactly on the dashed line, which is the line of force in our case. And then you have retrograde flow in between. Okay, so this one is the case where the forcing is doing everything. It's not that interesting and probably completely irrelevant for planets. So this is the last step of the reduction I will have to do. So if I want to compute the Reynolds stresses from the Rossby wave, especially to understand the second regime, why do I get a second regime? And I'm not just always have the first regime where all the jets are sitting on the forcing scale. I need to go a little bit beyond that, and I need to solve for the fluctuation. I need to understand what the fluctuations are doing, and in particular, what is the feedback of the zonal flow onto the fluctuation, onto the waves. So you need to work with this equation, which is not the full equation for your perturbation. Here I've made an assumption, which I call quasi-linear here, which is basically assuming that through my Reynolds decomposition, I have several coupling terms between the mean flow and the fluctuation. I will keep this guy, which is the advection of the fluctuation by the mean flow, which from the point of view of our model is linear, effectively, because we use a linear decomposition between the mean flow and the fluctuation. I'm neglecting here a term, because here it's beta, it's the same beta I had before, which is not true, because now I have a zonal flow, so I have shear in my system, which is effectively correcting the gradient of potential vorticity, but I'm neglecting this term here. It's not necessary to understand the transition, but it's an assumption. I have my friction here. You can keep dissipation if you want, and then you have forces. And of course, something very important here is that I'm completely neglecting eddy-eddy interaction. Okay, there's another nonlinear term, which is Rossby wave interacting with other Rossby wave, leading to other Rossby waves through resonances. I'm just neglecting that. Okay, I'm ignoring this part of the dynamics. So the only real feedback I have is the advection of the fluctuation by the mean flow. That's what I keep in my problem. So it becomes effectively linear. So you can, like, basically quite trivially, you get now Doppler shifted Rossby wave. You still have your linear restoring force, but now it's modulated by the fact that you have a mean flow that can advect your waves. So you get these Doppler shifted waves. So at this stage, there's still nothing you can really do with this equation. But you have, if you assume some simple forcing, you can do the calculation all the way through. So here, the assumption I'm going to use, which is quite sensible when you see the forcing in this experiment, is to assume that this guy is some kind of monochromatic forcing with one well-defined wavelength. So here I'm choosing like a wave number KF. And if you do this assumption, then you can do a nice Fourier analysis of this equation and fully compute what is the linear response of the fluctuation, and then compute the Reynolds stresses, because you analytically know what is the linear response. So you get the full Reynolds stress tensor, which is a function of the mean flow now. Okay, so if the mean flow back reacts on the wave somehow, it is included into this model. And clearly you can see that this is the overall solutions that you get. So this is the Reynolds stress driving your mean flow. And you can see it's some kind of a Lorentzian with a resonance kind of curve where if this guy is equal to -1, okay, these terms drop, and this is where your Reynolds stress will be maximum. So we have a resonant kind of behavior, and it's quite obvious what it is. Waves are propagating with a given phase speed. If this phase speed is opposite to the mean flow, then you expect the wave to be steady. Okay, if they are steady, they are sitting on a steady forcing, it becomes resonant, and it leads to divergence in the Reynolds stress. Okay, so you get a simple linear resonance of Rossby wave advected by your mean flow. So you can plot what the two driving terms in your mean flow equations are. So this is the Reynolds stress, this is the Lorentzian I just mentioned, and this is the friction term, which is alpha u. So it's a linear term, and I plot here these two terms versus the mean flow amplitude. So when the first regime, the one when you have only weak jets, is a regime where basically the intersection between these two curves, which is your steady solution, is at the bottom left here, very weak mean flow. Okay, there's no intersection between your friction term and the peak in your Lorentzian, so when the resonance occurs. So this is the first regime. The second regime is where you have basically the only intersection is above the resonance. Your peak is so high that the only intersection you get is this one. And then, of course, in between, you have this regime where you have three intersections. Okay, so one which is reminiscent of this one that is reminiscent of this one, but now you also have an intermediate solution, and this one is, of course, unstable. You can show it analytically, it's quite simple because of the curvature of this landscape here, it is unstable. So this solution you never see in this guy. So the bifurcation we saw is between these two states that can be eventually bistable in some region of parameter space, where you have three possible intersections between the Reynolds stresses, which can be resonant with the mean flow itself, and the damping mechanism, which is here linear drag.
Do you calculate how the wave energy changes?
So that's something we would like to do. So it's
I mean, it must, right? Because it generates the flows, so there's conservation of energy.
Exactly. So,
and you should. Well, and then you're back to our beloved game of the LH, or not even the LH transition, but the predator prey.
Exactly. So that's something we can do in numerics, because we have like all the averaging and the resolution we need in the experiment, where we try to play this game of extracting amplitude of the noisy field and trying to look at the time evolution. It's a little bit messy. So like our measurements are not accurate enough to have to clearly see, for example, how the waves amplitude change as it resonates with the mean flow, etc., etc. But in simulation, you do see that quite clearly, and you do have some prey-predator kind of dynamics when you are in this kind of regime. At the transition, it looks like the zonal flows can grow, waves start to drop, but then it goes back because waves radiated enough momentum. Then it's a kind of intermittent dynamics when you're right.
In other words, you get a limit cycle state.
So that, I don't know. I don't know if you get limit cycle or if it's like a on-off intermittency. Or I have no idea. We don't know what the dynamics is around this condition. And so you can look at this simple theory here. The only unknown you have in your model is this gamma and this C coefficient. This is fixed. This is coming from the forcing pattern in our experiment. This is all known, and this is a friction parameter, which we also know in this reduced model. It's only related to the Ekman number. So we know all of these numbers in the experiments. We can plug them, look at the two solutions we get, U1 and U3 here. And this is the two value we get. U1 is either 3 millimeter per second or 7 millimeter per second, which is roughly the two different states that we get. Okay, so we're happy enough. You can actually look a little bit more into the details to convince yourself that this transition is indeed the one we see in the experiment by looking, for example, at is the Rossby wave resonating or not, meaning are the phase speed comparable or not with the mean flow. And indeed, when you're here, the flow is not fast enough to Doppler shift the wave strong enough so that they become resonant, and here they are.
The alpha parameter?
So the alpha is just here in the experiment, a little bit more complicated, but in the reduced quasi-geostrophic model, it's purely due to the reconnection of your 2D flow onto the bottom boundary through an Ekman layer and Ekman pumping. So at this linear level, it's a linear drag term that depends on this Ekman number, on the square root of the Ekman number.
My question was more on the experiment.
So in the experiment, it's a little bit more complicated because I don't have time to explain, but our bottom is not flat. So we don't have a regular Ekman pumping. We have a little more subtle Ekman pumping. The reason why it's not flat is, I can explain it, but it's in order to have a constant beta effect. So it's a technical side. But yeah, it's not flat, so we have to take into account for the angle of the slope. But all can be done at all this theory can be done at the linear level at least. So the main assumption is that everything can be explained with linear arguments here. Okay, if for some reason the flow is more turbulent than we think, and the boundary layer is maybe not that laminar, then maybe we make a mistake on this estimate.
Is there a critical forcing you need to get the transition? I
Yeah.
would imagine if you go to very weak forcing, your hysteresis region would collapse and you just have an inflection there.
So okay, see what you mean. So the critical parameter is not the forcing, it's the Ekman number. If your Ekman number is not low enough, then you never get this because you're always overdamped basically, and the resonance can never have this crossing. So which is why I believe this has not been seen before in experiment. This has been seen in many numerical models, this kind of resonant behavior, because they're always in the low friction limit. It's quite easy to put yourself in a numerical simulation to see that, but in experiments you need very low Ekman number.
You mean by having stressful boundary condition rather than no slip?
So if you do like let's say a 2D model of this, a QG model, and you completely forget about the Ekman pumping, it's even there's no friction. The only thing that is damping your system is viscous, like the volume viscous terms. So it's effectively like alpha goes to 0, so you get so it's very easy to get this kind of dynamics. As soon as you put some friction, and you always do in experiment, then this is where it starts to be very difficult to see this kind of dynamics because of the fact that the friction term is dominant. So it's really dragging you down and then preventing you to see this kind of asymptotic dynamics. Yeah, because of no slip. So to conclude, we can get dominant or at least equipartition between zonal flows and fluctuation in such an experiment, but basically there's no way around it. You need to force to have large experiments that are rotating quite fast. Clearly, the only improvement we can make is basically reducing the friction as much as we can, okay, on the bottom. This is the only thing that could push us a little bit more in the asymptotic state, but this is extremely difficult because getting rid of a boundary is difficult. So we can get rid of one, but then, okay, it's the second one, we need to keep it somehow to prevent water from falling down. So unfortunately, it's going to be difficult to remove it. So we see that we have two regime of jets. We believe that most previous experiments were in the force regime with a very strong correlation between the forcing and the jet pattern. But there is eventually, if you're at low Ekman number, a secondary regime, which is probably much more dynamical and relevant for geophysical flows, because now the jets have their own nonlinear dynamics. They feed on the wave. and can like merge, grow in amplitude, in size, drift, etc., etc. They have like more like a richer dynamics, which at least close to the transition we saw can be understood with just Doppler shifted Rossby waves. So we just need to take into account the advection of the wave by the zonal flow itself to be able to see this, to understand this resonance. So it is actually quite a well-known problem in atmospherical science as a famous problem of the block jet stream, which is relevant, which is quite similar, where you have like a resonance between mean flow and Rossby waves. And also a recent study that is very, very reminiscent is the problem of equatorial superrotation. It's exactly the same. Is when you start to concentrate the angular momentum of your atmosphere into the equator. And this is also highly dependent on resonances between Rossby wave and mean flow. So this is all pretty much connected. Some things that, as David asked, here our system is a stationary pattern, which is not very geophysical. Okay, we have like a rotating planet, and we have a fixed pattern that is forcing the system. And we believe it's crucial to the transition we see, and that clearly what needs to be done is to address the question of what is the role of the forcing here. If we had a more realistic forcing, something that could, for example, be advected itself by the mean flow, like an instability, then maybe we won't see the resonance at all, because the forcing will never be stationary. So everything is advected by the mean flow, so that you can really never phase lock Rossby wave with the forcing. Or maybe you can, but at least in a different way to what I just described. So the role of the forcing is really important, and it's something that we need to explore. And something that is really not clear is that the experiment we saw merging and drifting, and this is something that I've been seen in many numerical simulations, and it's quite difficult to try to understand why do jets merge, when do they merge, when do they drift instead, do they push one another, the multi-jet solution and how they interact. Once you're in this steady state of strong nonlinear jet, it's not really clear. And I have some perspective. I would skip that. Something that I didn't really discuss, but it's quite interesting, that we clearly see multi-stabilities. These are 3 experiments, same control parameter, just 3 differential conditions. As I said, you have different like position of the jets, different equilibrium possible. Is this really multi-stable, or do you jump from one another, or we don't know? But it's quite reminiscent to what have been obtained in simple 2D barotropic model by Eric Simonet, Jean Roland, and Frédéric Boucher, where they solved the 2D vorticity equation on a simple square box. They waited for ages, and they saw some kind of transition between 2 and 3 jets, jets changing position. There is a sign of multi-stability in the system, but it's not really clear yet.
One question with respect to that. Are we always getting to a lower number of jets, or do we have instances where jets could split?
So here they do have both have merging and splitting, because they alternate between 2 states, like a 2-jet state and a 3-jet state. And they go stochastically from one to the other, and they understand it's a noise-induced transition with instantons and all this kind of game. So they understand this transition quite fair. It's not exactly the same as in our case, but it's probably because this is not at all in the same limit. This is in a very low forcing, low friction limit. We are in the strong friction, strong forcing limit. So this is probably the reason why we only have steady states, and there's not enough noise to jump from one solution to the other, because we're still frictionally dominated, whereas they are not. And then, as Pat mentioned, then we have these weird kinks, and we see them grow, and then if you fix a position, you see that they grow, and then it's like they launch at quite a large phase velocity. We don't really know what these structures are. We also see them in reduced models. They correspond to highly nonlinear Rossby wave breaking, and leading to some kind of a nonlinear dynamics that is quite subtle. So in the literature, some people see this structure as a solitary Rossby wave. There is some dispersion, but because of the presence of the zonal flow, both can compensate and lead to solitonic kind of Rossby wave. We don't know if that's the correct way of viewing that, or if it's something else. But it's something we quite robustly see with some like well-defined period that appear in the system, which is alternating between no such structure and then such structure appearing, launching, and dissipating. It's not exactly clear.
Do these things ever get energetic enough to interfere with your transition between the different states, or, for example, knock you out of the higher state? You see, in other words, if you imagine you go to a state where you have a lot of energy in the flow, is the question is, does that can that in some sense be unstable or otherwise unfavorable that would then knock you back to a lower?
Yeah, I
flow
see.
state?
So maybe
This is of great interest to us. By the way.
of course.
Yeah.
Then let's call that LH transition.
Well, no, I mean, it's actually more related to the question of stability of the zonal flow.
So in our case here, we are in a regime where basically there's no spontaneous transition between the two regimes. If you put yourself in a control parameter, you're either in one or bistable, but you never have spontaneous transition, at least from what we could see in the experiment. Maybe it's just a time problem. If we waited long enough, it's like a rare event. If it's like noise induced, I just have to wait long enough. So maybe we didn't wait long enough to see spontaneous transition, but it seems probably because we are dominated by friction, then the basin of attraction of the two are well separated, and the noise is not enough to jump. But like, let's say we could reduce the friction even further, maybe this would happen. We don't know. Unless the last thing we want to measure, and something that is of great importance in oceanography, is plasma physics also, is how these zonal jets, now that we have asymptotic zonal jets in an experiment, can we actually measure transport barrier in an experiment of zonal flows? Yeah, so this is something we already did. So it's a mixed approach where we use the velocity field from the experiment, we put some passive tracers in it, we advect it by the experimental flow, and we look at how it's dispersed. Okay, and the game is to basically try to find if there is a strong correlation between the turbulent diffusivity of this passive scalar and the existence of jets. Okay, and of course, the answer is yes, and we would like to quantify that in an experiment to have like a eddy, to see if we can measure experimentally eddy diffusivity suppression due to jets. Okay, and it's something that we are working on right now. And I will stop here. Thank you very much.
Questions? Questions? Norman.
So to clarify, do you see any sort of inverse cascade into longer scale velocity waves, or are there ways to turn there?
So in experiments, it's always difficult because all the length scale are very close to each other. But basically, using simulation, we can extrapolate a little bit from what we can achieve in the lab. And yeah, the correct picture is indeed we have a forcing length scale. There is some tendency for an inverse cascade. In the experiment, the two scales are very close because, as you saw, we have 6 rings, and then we end up with 3 jets. So I wouldn't like qualify that as a scale separation enough to say if I have an inverse cascade, but you can play the same game with numerical simulation, like increase the scale separation. And yes, you have a forcing scale. Initially, it's just an isotropic inverse cascade feeding some large scale structure. Then you start to interact with Rossby wave once your scale large enough, and then you have the zonal the zonation of this inverse cascade. But in the experiment, everything is a little bit on top of each other, so it's difficult to quantify it.
You started asking the question with Jupiter. But then with Jupiter, you probably need to relax being homogeneous in the vertical, right? You probably need this 3D convection. So have you relaxed, or at least before doing that in experiment, try to do it numerically, and how much, not being homogeneous in the vertical would actually impact what you see?
So in all of the different predictions I've made, the most relevant one, which is coming back from the experiment to Jupiter, I didn't discuss it at all because, of course, it's the most difficult. Mm-hmm. So clearly, we are really far, okay, in terms of like a dynamical regime. Even if we see this transition, and we could argue, oh, now we reach a new state, we're really far. Reynolds number are still very marginal, so we don't know. And clearly, there's plenty of very important ingredients missing for Jupiter. So the atmospheric structure, like the radial structure, is of course fundamental. Okay, because you have large density variations, then you go from weakly conducting to a dynamo region, which seems to act as a drag on the jets. I mean, you have all this complicated layer structure that needs to be taken into account. For example, in the experiment here, I've said, oh, the friction is clearly Ekman pumping. It's not Ekman pumping on Jupiter. There's no solid wall anywhere. So it's some complicated coupling with a deeper layer that leads to the stationary state. So there's plenty of missing ingredients that makes the application to the problem very difficult.
There is a solid core, possibly.
Yeah, but much deeper the dynamo region. So probably the
The problem of Juno is that it demonstrated that the zonal jet region is only 3,000 kilometers deep, which used to be much deeper initially.
well, it depends. I mean, if you think of the, I mean, some people said it's only in the cloud layer initially, which is like a few tens of kilometers or hundreds of kilometers. So for me, 3,000 kilometers, sorry, for me it's deep, because the depth is roughly equal to the thickness of the jet. So I mean, saying that these structures are two-dimensional, I mean, of course it's not deep at the scale of the for the scale of the planet, but in a dynamical sense, should we model this as a 2D shallow structure or barotropic structure? It's not clear.
And it was, we know Bussy colon, we were expecting them to be much deeper if we were expecting Bussy colon, because on the polar ones, if you take the tangent cylinder, you will be much deeper than the 3,000 kilometers.
But there's no, I mean, we knew that the Bussy vision was a little bit simplistic because there's no dynamic regions, there's no, it was for a purely barotropic system with no density variation. So we knew that it couldn't go as deep, just due to argument of conservation of angular momentum.
I was asking a much simpler question. I'm not
sorry.
asking that you do an experimental Jupiter. I'm just asking if you put a little bit of three-dimensionality, how does that affect?
I see. So right now, there's another PhD student working on the same setup, but we basically did the simplest step toward a non-purely barotropic system, so purely depth invariant. So the thing we do is we basically have a two-layer system, okay, with two different densities. Okay, so it's a first step from having a non-depth invariant system. We have salty water at the bottom and then fresh water at the top. Okay, and we don't play this game yet. We do something simpler where we look at the dynamics of vortices on the upper layer. This is mostly related to the polar dynamics where we see clusters of cyclones. But eventually we'll do this. We'll repeat these experiments, but in a two-layer system where we either force the jets in the bottom region and see what happens at the top, or the other way around. And that would basically try to close a little bit the debate. What is the energetic origin of the jet? Is it due to baroclinic instabilities in the atmosphere that then propagate inward? Or is it deeper convection that propagate upward? Or is it both? Probably both. But
So, historical question. I mean, if we delve into ancient history, there are these old works by Bussy, which I mean have a very similar flavor to. I mean, of course, it's thermal Rossby, but I mean you get a critical Rayleigh number, you get a drop in the Nusselt number, and an advance in the flow. I mean, it's much. Is it fundamentally the same story apart from the difference between the difference in the forcing or excitation mechanism?
So I think most of the previous experiments, so when something was driven by instabilities, it's a little bit more difficult to address because of the fact that the instability itself depends on control parameters. So as you sweep in parameter, the landscape changes. But apart from that, I would argue that if you just look at the Ekman number of most previous experiments, I would be very surprised if they were in the second regime, meaning that they could achieve strong enough zonal flow to basically compensate for the phase speed of the Rossby wave.
I'm talking about, it was just theoretical work. I'm not talking about the experiment, but they did in the theoretical work.
Theoretical, yeah, sorry, yeah.
They do essentially
of course
find a state of high flow.
Exactly.
Very important, not only high flow and reduced Nusselt number, so reduced transport at high Rayleigh number, which it's
this sorry, I didn't understand. Yeah, for the theoretical part, yes, this is very reminiscent. This kind of transition has been seen in many models. I mean, by Charnay, Devore, so them as a it's a well-known problem in atmospheric science where you get very different jet response if the waves are super or sub-resonant. This is observed. You can measure the phase speed of Rossby wave on Earth. You can do it on Jupiter and Saturn. You can see whether you're super resonant or not. And this is a very important problem to see, will you have strong self-amplified jets, or are they completely blocked by the fact that they cannot advect Rossby wave fast enough? So from the point of view of the theory, it's completely understood.
No, it's connected actually. Do you see the retroaction of the zonal flows on the background turbulence, like vortex TVs, and which will actually be related to
question of energetics and also reduction of transport. Which of course is
So yes, in simulation, yes, we do. So
simulation, I guess.
yes, in experiments, it's very hard. Experiments, it's very difficult because measurements are too noisy for this kind of measurement. Or at least we would need like a lot of data to be able to average the noise out and get this kind of effects. It would be maybe possible if we were to put ourselves in another regime where we explicitly force the jets to clearly put only 2 jets in the experiment, and then we might have enough scale separation to see something. But the problem is that we lack scale separation. So jets, eddies, everything is more or less at the same length scale, strongly interacting. So you can statistically separate them out, but then the coupling is very strong. So it's difficult to, it's very noisy. Like measuring the eddy, just the Reynolds stress, for example, it's very hard to just average the noise and get a meaningful signal from the experimental data.
Get in a quick comment there. I think it's very important to look at the Reynolds work on the fluctuations, which, by the way, has to conserve energy with the Reynolds stress effect. As a more telling test than just the passive scalar transport, right?
Ah, yeah, of course. No, that I agree. I mean, here, for example, in the modeling of neglecting the fact that the zonal flow should also change the beta effect. I mean, this could be another way of saturating the system, just like
that leads to the question of stability.
exactly.
Yeah.
So, and I didn't address that at all.
In your experiment, you have 6 rings of the forcing. If you were reducing this number of rings and still doing the game of increasing the forcing, would you have the transition at the same amplitude?
So numerically, I mean, experimentally, we can't do that, but we have is, yeah, I have it. But numerically, you can. So here, it's basically just a simulation of the 2D reduced model I've used, and this is just exactly the same as in experiment, but now we don't have 6 rings, we have I don't know how many. Okay, and this is a stationary pattern we get. Okay, we get something very similar with more or less 3 jets. They have the same amplitude and energy, even though the scale separation is much larger. So it's just that in the experiment, we're just on the verge of scale separation, and it's not very clear. But at least when we reduce it numerically, then we don't see significant behavior. One thing that differs is that when you look at the like the nonlinear structure propagating on the jets, they are not the same. Because of course now we have more scale separation. We perturb the jets a little bit differently, so it's not the same. But at least from the point of view of the amplitude of the zonal flow, etc., it is rather independent of the scale of the forcing through the inverse cascade. But in the experiment, we can't prove it.
It's related to the question of Peter. So I understand that we plan to look at the impact of the forcing, or yes, do you plan actually to study also the phase shift between your mode, say azimuthal mod numbers that you put on the rings, shifting them by some amount to see whether there's a kind of an optimum to for the energy of the flow.
So one thing we did try is to instead to have a steady pattern, which is indirectly at the origin of the resonance. It's because we have a steady forcing. Once the mean flow opposes the phase shift of the waves, then you have a steady Rossby wave, which resonates with the steady flow. If instead of a steady forcing, we, for example, replace it by a fluctuating one, so pumps are going on and off in an alternating way, you still conserve the overall mass, but you just randomly change what is a sink and what is a source. If you do that, you still see the resonance, but not at the same position. Okay, probably because you add some stochasticity to, so it's more difficult to get the phases right, and so it's not the forcing we picked definitely has an effect on where does the transition occur, and I believe that the fundamental mechanism is quite universal, and you will see it in all systems, but our system is probably very efficient at driving this transition because of the stationarity of the force. If it's fluctuating, start to be different. If it was, like as you said, like if it was itself, the forcing had a phase, for example, because let's say it could be also advected by the mean flow, then you will have like a non-homogeneous resonance depending on where you are, and this would be probably another story also. But that we plan on doing probably numerically. It will be easier to mess with the forcing numerically than into the experiment, which will be very difficult.
Well,
So with the simulation of Jupiter and the observations, you know that the alternation is linked to the Rhine scale. And that's a little bit the piece I'm missing if your experiment, in the sense that you have a certain number of rings, but I'm not sure, it's not so clear to me how this number of rings is related to the parabolic shape of your free surface, like in Jupiter's or Saturn's jets. It's linked to the fact that you have a shallow layer and Rhine scale that explain most of the layering. So have you tried to make the connection?
Yeah. So you can try to plug like the zonostrophy theory, like turbulence theory, to see if it matches our experiment. On like to make a long story short, it does. It makes sense. But again, we are very far from the hypothesis of this theory where we need scale separation both between the forcing and the Rhine scale, and then another scale separation between the Rhine scale and the dissipation length scale. You need friction to be negligible at the Rhine scale, otherwise your jets will remain weak, even if they are far from the forcing. And so this double limit is completely impossible to reach experimentally. We are basically, the forcing length scale is twice smaller than the Rhine scale, and our dissipation length scale is twice larger than the Rhine scale. That's the kind of scale separation we have. But if you accept this, we do have some spectral properties that are reminiscent of the zonostrophic turbulence. But it's very, we have like power laws of less than a decade. So it's not very convincing.
Experiment, and don't get me wrong.
No, but it's a fair point.
To connect with
Yeah. And also our problem is that what is fixing the jet length is probably some confinement effect. For example, you always see a jet here, and it's due to the interaction with this boundary. Okay, so this jet is actually locked in some sense, so it's always there. So which means we only have like 2/3 of the domain, but so everything, and this is of course quite singular. The center is everything is, this is far from a free beta plane dynamics where the jets can do what they want. No, they clearly have confinement effect.
So astrophysical disks have Rossby number like half. So I was wondering how much room do you have in your experiment? You can maybe reduce the box rotation a little bit, but really increase the thrust of your jets. So you can get number. Yours is like -3.
Yeah. There's definitely room if you're interested in the moderate or order 1 Rossby regime. That we can do because we just need to crank up the pump. So that's easy to do. So increasing the Reynolds number and accepting the fact that the Rossby number is going to be order 1, this is something we plan on doing, because then this shouldn't be well modeled by quasi-geostrophic in the quasi-geostrophic approximation. We start to have real three-dimensional effects, which will lead potentially towards a transition. But then it's much more complicated because you need three-dimensional measurements to quantify them.
Do you ever see the surface deviate from some constant profile?
So you can measure that, but we are in the limit where it's negligible, meaning that the variation of pressure inside the fluid are small perturbation because of the smallness of the Rossby number and the fact also that the gravity is still dominant. So we have some fluctuations that are completely negligible. We are in the so-called quasi-rigid limit where you can assume that the upper surface is rigid. Okay, no gravitational wave, no gravity wave at the surface.
Is it ever possible to change water to liquid sodium?
So French are specialists of that, but no, I don't think so. In the hope of driving a dynamo, definitely not.
Now, I want to jump on that because you mentioned something about what to modify your numbers, but you didn't mention reducing the viscosity of the fluid you are using. And water in the experiment is pretty much less viscid fluid you can add.
No, you can play with other fluids, but then they are not as nice as water. So you can. So the only choice you have really, if you don't want to breathe fumes and this kind of stuff, is basically silicone oil. Some silicone oil are twice less viscous than water, but the problem is that we need 600 liters of that. And this kind of silicone oil are not cheap. So it would cost a lot of money to buy.
A factor of 2.
And for a factor of 2. So
Let's thank you again for very
thank you.